What would happen if you tried to land on Saturn, only to discover there was no ground waiting beneath the clouds? Tonight, we'll follow the history of this extraordinary world, from its violent birth and mysterious rings to the storms, moons, and hidden depths that make it unlike any planet we know. Welcome to Sleepy Cosmic Lore. Please like and subscribe. It may seem small, but it truly means a lot to me. Thank you. Imagine approaching Saturn from the darkness beyond its rings. At first, it looks almost welcoming. A pale golden sphere suspended beneath a vast, shining disk. Its colors softer than Jupiter's storms, and its edges blurred by high atmospheric haze. From a distance, it resembles a world waiting to be visited. But as your spacecraft begins to descend, something unsettling becomes clear. There are no continents below you, no oceans reflecting sunlight, no mountains pushing through the clouds, nothing that can honestly be called land. The surface you thought you were approaching is only the visible top of an atmosphere thousands of miles deep, and the farther you fall, the less the familiar idea of a planet makes sense. Saturn is not a rocky world hidden beneath a layer of clouds. The clouds, the gas beneath them, the compressed fluids below that, and the strange metallic material farther down are all part of the planet itself. There is no simple boundary where the sky ends and the ground begins. That is why Saturn is not merely difficult to land on. In the ordinary meaning of the word, there is nowhere to land at all. A spacecraft entering Saturn would first encounter an atmosphere composed mainly of hydrogen, with helium making up most of what remains. At great altitude, this gas is extremely thin, fading gradually into space rather than ending at a sharp edge. Scientists therefore have to choose an artificial reference level when describing Saturn's size. They commonly use the altitude where atmospheric pressure reaches 1 bar, roughly the pressure at sea level on Earth. This level is sometimes treated as Saturn's surface, but it is only a measuring line drawn through the clouds. A spacecraft could pass through it without striking anything. There would be no impact, no dust, no sudden stop, only gas becoming steadily thicker around the hull. Even the beginning of the descent would be violent. A vehicle arriving from interplanetary space would be moving at enormous speed, and the atmosphere in front of it would compress so rapidly that the surrounding gas would become intensely hot. A heat shield might keep the craft alive for a time, but slowing down would only reveal the next danger. Saturn's upper atmosphere is not a quiet golden mist. Powerful winds race through it, especially near the equator, where speeds can reach well over 1,000 kilometers per hour. These currents flow in wide bands around the planet, driven partly by Saturn's rapid rotation and partly by heat rising from its interior. Because there are no continents, mountain ranges, or solid landscapes to interrupt them, the winds can travel around the globe with fewer obstacles than storms on Earth ever encounter. The spacecraft would be entering a world where the weather has no ground beneath it. As it fell below the highest haze, the light would begin to change. The gentle yellow seen from space comes from clouds and chemical compounds in the upper atmosphere, altered by sunlight. Deeper down, the sky would grow dimmer and more opaque. The first major cloud layer is believed to contain crystals of ammonia ice. Beneath it, under greater pressure and warmer conditions, may lie clouds containing ammonium hydrosulfide. Still farther below, models predict enormous water clouds, where heat and pressure could drive powerful convection, lightning, and storms hidden from every telescope on Earth. No probe has yet descended deeply through Saturn's atmosphere, so some of this layered structure is inferred from chemistry, physics, and comparisons with Jupiter. The broad picture is well supported, but the exact appearance of those depths remains unseen. That uncertainty makes the fall more disturbing, not less. A spacecraft would be entering a region no camera has ever photographed directly, surrounded by clouds whose scale could dwarf entire countries. Yet the clouds would not be the main reason the mission failed. Pressure would be. On Earth, people experience atmospheric pressure as the weight of air above them. On Saturn, that weight increases continuously as more and more gas piles overhead. At 10 times Earth's sea level pressure, a specially built probe might still function. At 100 times, the structure would need extraordinary strength. Deeper still, every seam, instrument, window, and electrical system would be tested from all directions at once. The craft would not be crushed by one dramatic blow. It would be squeezed steadily, relentlessly, while the temperature climbed around it. Long before it reached Saturn's deepest layers, the vehicle would almost certainly collapse, its materials breaking apart and mixing into the surrounding planet. But suppose, for the sake of the journey, that the spacecraft were indestructible. Even then, it would never reach a normal surface. As hydrogen is placed under greater pressure, it stops behaving like the thin gas used in balloons or fuel cells. Its molecules are forced closer together until the material becomes fluid-like. The change is gradual. There is no ocean surface to cross, no visible line where gas suddenly becomes liquid. The atmosphere simply grows denser until the falling craft is moving through something more like a strange, hot sea than a sky. This is one of the hardest things to imagine about Saturn. Human intuition expects clean boundaries: air above water, water above rock. Saturn does not respect those categories. Its interior is a continuous transition through forms of matter that rarely exist naturally on Earth. Farther down, the pressure becomes so extreme that hydrogen may enter a metallic state. In this region, electrons are no longer held in the same way they are in ordinary molecular hydrogen, allowing the material to conduct electricity. The motion of this electrically conducting fluid is believed to help generate Saturn's magnetic field. It is a world-sized electrical engine buried beneath tens of thousands of kilometers of atmosphere and compressed hydrogen. No person could see it directly. No conventional submarine could float within it. And no spacecraft built from familiar materials could remain intact long enough to reach it. Below that may lie Saturn's central region, often loosely called its core. Earlier diagrams presented it as a compact ball of rock and ice surrounded by clean layers of hydrogen and helium. The real structure may be far messier. Measurements of Saturn's gravity and subtle waves in its rings suggest that the central heavy material could be spread across a broad region, mixed gradually into the surrounding hydrogen rather than separated by a sharp boundary. Some researchers describe this possibility as a diffuse or fuzzy core. It may contain rock, metals, water, methane, ammonia, and other materials, compressed into forms that cannot be reproduced easily outside powerful laboratories. There is still debate over its exact size, composition, and structure. But even if some part of this deep interior is solid, or partly solid, calling it a place to land would be misleading. By the time anything reached it, the pressure would be millions of times greater than at Earth's surface, and the temperature would rise to many thousands of degrees. A spacecraft would not touch down there. Its atoms would have been scattered into Saturn long before. The phrase, falling into Saturn, can also create another false picture. The idea that someone might plunge through the planet and emerge from the other side. In reality, the atmosphere would steal the object's speed. Drag would slow it. Turbulence would tear it apart. And the remaining material would descend only as far as its density and the surrounding currents allowed. Different substances might settle at different depths. Some would vaporize. Some would dissolve into the hydrogen-rich interior. Nothing recognizable would continue along a clean path through the center. Saturn would absorb the intruder, not permit it to pass through. Strangely, gravity near Saturn's visible cloud tops would not feel as overwhelming as the planet's size suggests. Saturn has more than 90 times Earth's mass, yet it is also enormous, so its outer cloud layers lie far from the center of gravity. Its rapid rotation also slightly reduces the effective pull near the equator. At the commonly used 1 bar level, gravity is only somewhat stronger than on Earth. A person floating there would not instantly feel 90 times heavier. That apparent gentleness is deceptive. Gravity is not the immediate problem. The absence of solid ground, the extreme winds, the rising pressure, and the growing heat are what make the descent impossible. In theory, a floating probe might survive for a while in a carefully chosen atmospheric layer. A balloon could perhaps ride where pressure and temperature were manageable, collecting data while drifting through Saturn's winds. It would not be landing, however. It would be sailing through an atmosphere with no safe harbor beneath it. Eventually, it might be carried into harsher regions, damaged by storms, or forced downward as its systems failed. Saturn allows orbiting, flying, and falling. It does not allow standing. That is the deeper mystery hidden behind its beauty. From Earth, planets appear as solid circles of light, and the mind naturally imagines each one as another landscape, a place with a horizon, a sky, and something beneath your feet. Saturn breaks that expectation. It is a planet without a reachable floor, a world defined not by a surface, but by depth. Its visible clouds are only the entrance. Beneath them lies an immense progression of pressure, heat, fluid hydrogen, metallic matter, and perhaps a core whose boundary may be blurred across thousands of miles. To understand how such a world came to exist, we have to go back to a time before Saturn had rings, before Earth had oceans, and before the young sun had finished gathering itself from the darkness. Long before Saturn became the pale, ringed giant we recognize today, there was no planet, no Earth, and no quiet arrangement of worlds circling the sun. There was only a collapsing cloud of cold gas and dust, part of a much larger region where stars were being born. Gravity drew material inward, and as the cloud contracted, it began to spin faster, flattening into a broad disk around the young sun. Inside that disk, billions of collisions were already beginning to write the architecture of the solar system. Dust grains struck one another and sometimes stuck. Those tiny clusters collided again, becoming pebbles, then boulders, then objects large enough for gravity to take over. Yet Saturn's story could not have unfolded everywhere in the same way. Close to the young sun, temperatures were too high for water, methane, and ammonia to remain frozen, so the growing planets there had to build mostly from metal and rock. Farther out, beyond a shifting boundary often called the snow line, ice could survive. That changed everything. Ice was not merely decoration on distant worlds. It gave growing planetary bodies access to far more solid material. A young object forming in Saturn's region could gather rock and frozen compounds together, increasing its mass much faster than a body limited to stone alone. This is the central idea behind the leading model of Saturn's birth, known as core accretion. The name sounds simple, but the process was a race against disappearance. The disk around the sun was rich in hydrogen and helium, the same light elements that would later dominate Saturn. But that gas would not remain forever. Radiation and winds from the young sun, along with other processes within the disk, were gradually clearing it away. If Saturn's early core grew too slowly, the gas would vanish before the planet could capture enough of it. If the core grew quickly enough, however, its gravity could begin pulling in an atmosphere, and that atmosphere could eventually become so massive that gas started falling inward at an accelerating rate. Somewhere during that transition, Saturn stopped being merely a large, icy, and rocky body and became a giant planet. The exact sequence remains difficult to reconstruct because no untouched record of that moment survives. But most models suggest that Saturn first assembled a substantial central concentration of heavier material, rock, metals, and ices, before surrounding itself with the enormous hydrogen-helium envelope that now makes up most of the planet. How massive that early core had to be is still debated. Traditional models often placed the critical value near 10 Earth masses, but newer work suggests the answer depends heavily on how quickly solids arrived, how hot the surrounding gas was, and whether the material sank into a compact center or became mixed through a broad interior region. Saturn may never have possessed the neat, sharply bounded core shown in old textbook diagrams. Its beginnings may have been turbulent from the start, with incoming rock and ice dissolving, melting, or spreading into the growing envelope. Even the way Saturn collected its raw material is not fully settled. In the older picture, large planetary building blocks, called planetesimals, crashed into the young world, one by one. In another possibility, much of the growth came from pebble accretion, in which smaller particles drifting through the disk were captured efficiently by the gravity and gas around the forming planet. Pebbles sound insignificant, but in a disk containing vast amounts of material, a steady river of them could build a planetary core surprisingly fast. This may help explain how giant planets formed before the gas disk disappeared, though researchers continue to test how well the process works under the conditions thought to exist near Saturn. There is also a more dramatic alternative known as disk instability. In this scenario, part of the gas disk could have become gravitationally unstable and collapsed directly into a giant clump, forming a planet rapidly without first constructing a massive, solid core. Such a process may occur in some planetary systems, especially in massive, cold disks far from their stars. Whether it played a major role in Saturn's formation is less certain. Saturn's enrichment in elements heavier than hydrogen and helium, together with evidence for a substantial central region, generally fits core accretion well. But the early solar system was complex enough that the final answer may not belong to a single, clean mechanism. A rapidly collapsing gas clump could still gather solids later, while a core accretion planet could experience episodes of sudden gas capture that looked almost like collapse. Nature does not always respect the categories used to describe it. What seems clearer is that Saturn did not form alone. Nearby, Jupiter was growing faster and becoming more massive, and its gravity would have reshaped the disk around both planets. As Jupiter opened gaps in the gas and altered the movement of smaller objects, Saturn's access to material changed. The two giants may have influenced each other's growth through resonances, waves, and competition for gas. This relationship could explain one of the most important differences between them. Jupiter became more than 3 times as massive as Saturn, even though both are dominated by the same two elements. Saturn may have begun later, grown in a region with less available gas, or had its supply restricted by Jupiter's earlier rise. It is also possible that Saturn's own growth changed the flow of material in ways that limited its final mass. The result was not a failed Jupiter, but a different kind of giant, lighter, less compressed overall, richer in some heavy elements, and shaped by its own thermal history. Its low average density is a consequence of this composition, though the familiar claim that Saturn could float in water is only a playful comparison. No ocean could hold it, and a body that large would distort any imaginary sea through gravity. Still, the comparison captures something real. Saturn contains so much hydrogen that its average density is lower than that of liquid water, even though its interior is compressed into states far denser than anything at the cloud tops. The planet's enormous size therefore hides a peculiar balance: vast volume, tremendous mass, and a composition dominated by the lightest element in the universe. While Saturn was gathering gas, it was also releasing heat. Every falling object converted gravitational energy into warmth. Gas collapsing inward was compressed. Collisions, differentiation, and the settling of heavier material all contributed to a young planet that was larger, hotter, and brighter in infrared radiation than Saturn is now. It may once have glowed faintly from its own formation heat, invisible to human eyes, but detectable as thermal radiation, had any observer existed nearby. Over billions of years, Saturn contracted and cooled, yet it never became cold inside. It still gives off more energy than it receives from the distant sun. Some of this comes from slow gravitational contraction, as the planet continues to compress and convert that change into heat. Another contribution may come from helium separating from hydrogen in the deep interior. Under certain pressures and temperatures, helium may become less soluble, forming droplets that sink and release energy as they fall. This so-called helium rain is a leading explanation for part of Saturn's excess heat, though the exact behavior of hydrogen and helium under such conditions remains an active area of research. Saturn's birth also left a chemical signature. Compared with the Sun, its atmosphere is enriched in carbon and probably other heavy elements, evidence that the planet did more than simply scoop up surrounding gas. It also swallowed large amounts of icy and rocky material. Some of that material may now be buried deep inside, while some was mixed into the envelope. Determining exactly how much heavy material Saturn contains is difficult, because scientists cannot sample its interior directly. They instead study its gravity, shape, magnetic field, atmospheric composition, and even waves traveling through the rings. Each measurement offers a different clue, and the clues do not always fit a single, simple model. Saturn may hold the equivalent of many Earth masses of heavy elements, but how those elements are distributed remains uncertain. A compact core, a broad, dilute center, and layers with gradual changes in composition can all produce somewhat different versions of the same planet seen from outside. Then there is the question of location. Saturn may not have remained where it first formed. Young planets interact gravitationally with the disks around them, exchanging angular momentum with gas and drifting inward or outward. Giant planets can also scatter one another and rearrange smaller bodies. Several models propose that Jupiter and Saturn migrated significantly during the solar system's youth. In the grand tax scenario, Jupiter moved inward before Saturn's growth helped reverse the motion, with both planets then migrating outward. This could help explain the small mass of Mars and the mixed composition of the asteroid belt, though the model is not universally accepted in every detail. Later, in versions of the Nice model, the outer planets may have shifted again after the gas disk disappeared, destabilizing populations of icy bodies and contributing to the present arrangement of the outer solar system. These ideas are powerful because they connect Saturn's history to everything around it, but they remain reconstructions rather than eyewitness accounts. Computer simulations can show what is possible and what is likely under certain starting conditions. They cannot tell us with certainty which exact path nature followed more than 4 billion years ago. Still, one conclusion is hard to escape. Saturn's current orbit is not simply an address where it quietly assembled and stayed. It may be the final position reached after a long period of movement, competition, and gravitational negotiation among newborn worlds. That restless beginning may also have shaped Saturn's moons. A disk of gas and solid material likely surrounded the young planet, functioning like a miniature version of the disk around the Sun. Within it, moons could form, migrate, collide, or fall into Saturn. The satellites visible today may not be the first generation. Some could preserve ancient material from Saturn's earliest years, while others may have been rebuilt or transformed by later collisions. The rings, too, probably did not appear in their present form at the moment Saturn was born. Their origin belongs to a later and more uncertain chapter, possibly involving the destruction of a moon, the breakup of an icy body, or repeated cycles of formation and loss. The Saturn that emerged from the solar nebula was therefore not the finished masterpiece seen through modern telescopes. It was a hot, swollen, evolving giant, surrounded by debris, embedded in a changing disk, and locked in a gravitational relationship with Jupiter that may have altered the destiny of the entire solar system. Over time, the gas around the sun cleared, the planets settled into more stable paths, and Saturn cooled into the muted world we know. But for almost all of human history, none of this could be seen. The violence of its formation left no obvious mark to the naked eye. From Earth, Saturn became only a steady golden point moving slowly against the stars, distant enough to appear calm, simple, and almost timeless. The next mystery was not how it had formed, but how a world so enormous could hide its true shape from every human observer until a crude telescope finally revealed that the lonely light in the sky was not alone at all. For thousands of years, Saturn revealed almost nothing of itself. It appeared as a small yellowish light moving slowly against the fixed stars, visible without any instrument and distant enough to seem calm. Ancient skywatchers recognized that it did not behave like an ordinary star. Night after night, month after month, it shifted its position along the zodiac, sometimes appearing to slow, stop, and move backward before continuing on its path. The motion was an illusion created by Earth and Saturn traveling around the Sun at different speeds. But to early observers, it made the object feel alive, a wanderer following rules no one yet understood. The Greeks associated it with Cronus, the old god of time, while the Romans linked it with Saturn, a figure connected to agriculture, cycles, and a vanished golden age. Those meanings were cultural rather than scientific, yet they reflected something real in the planet's appearance. Saturn was the slowest of the bright wandering lights known to antiquity, taking nearly 30 Earth years to circle the sky. A human could watch it complete only 2 or 3 orbits in an entire lifetime. For ancient astronomers, it marked the outer edge of the visible planetary system. Beyond it lay the supposedly fixed sphere of stars and whatever mysteries human eyes could not reach. Even careful records from Babylonian, Greek, Indian, Chinese, and Islamic astronomers could reveal only its movement and brightness. No one saw its rings. No one saw its moons. The most visually extraordinary planet in the solar system spent almost all of recorded history disguised as an ordinary point of light. That disguise began to fail in 1610 when Galileo Galilei aimed one of his early telescopes toward Saturn. The instrument was revolutionary, but its image was small, unstable, and distorted by lenses far inferior to those used today. Galileo could see that Saturn was not a simple round disk, yet he could not determine what surrounded it. He described the planet as having companions on either side, almost as though 3 bodies were touching one another. In one interpretation, Saturn appeared to possess 2 large moons pressed close to its body. In another, it looked like a planet with handles or ears. The strange attachments did not move around Saturn as normal moons should, and Galileo had no physical model that could explain them. Then the mystery deepened. When he observed Saturn again in 1612, the objects on either side seemed to have vanished. The planet appeared alone. Galileo was stunned. He wondered whether Saturn had somehow swallowed its companions, or whether his earlier observations had been misleading. 2 years later, the side structures returned, now looking more like curved projections. What Galileo could not know was that he was witnessing the changing angle of the rings. Saturn's axis is tilted, so as both Earth and Saturn travel around the Sun, the rings appear to open wide, narrow, and eventually turn almost edge-on. Because the main rings are extremely thin compared with their enormous width, they can become nearly invisible through a small telescope when viewed from the side. The objects had never disappeared. Human vision had simply encountered a structure so unfamiliar that the mind tried to force it into known categories. Galileo's failure was not foolishness. It was a reminder that discovery often begins with seeing something correctly, but interpreting it through the wrong picture. The answer came several decades later through Christian Huygens, a Dutch mathematician, physicist, and astronomer who had access to better telescopes and more refined lenses. In 1655, while studying Saturn, Huygens also discovered Titan, the planet's largest moon. The following year, he published the explanation that transformed Saturn from a visual puzzle into a new kind of world. The planet was surrounded by a thin, flat ring that did not touch it and was tilted relative to the plane of Saturn's path. This model accounted for the changing shapes Galileo had seen. When the ring was open toward Earth, it produced the appearance of two broad extensions. When viewed edge-on, it nearly vanished. The solution seems obvious now, only because Huygens supplied the concept that earlier observers lacked. At the time, nothing else in the known heavens looked remotely similar. A planet encircled by a detached ring was not merely a new detail. It was a direct challenge to the expectation that celestial bodies would fit a small number of familiar forms. Yet, Huygens had not solved the entire problem. Through the instruments of the 17th century, the ring looked like a single, continuous structure, almost like a solid disk with a hole in the center. That picture began to fracture in 1675, when Giovanni Domenico Cassini observed a dark division within the ring system. The broad gap, now known as the Cassini division, separates the brighter A and B rings, though it is not completely empty. Its existence revealed that Saturn's ring was not one uniform object. Cassini also discovered several of Saturn's moons, including Iapetus, Rhea, Tethys, and Dione, turning the distant planet into the center of a complex miniature system. Iapetus presented a mystery of its own. It appeared much brighter on one side of its orbit than the other, leading Cassini to suggest that one hemisphere was darker and that the moon kept the same face directed along its path around Saturn. Both ideas were remarkably perceptive. Long before spacecraft confirmed the moon's two-toned surface, careful observation had already shown that even the faint points around Saturn carried histories written in light. As telescopes improved, more ring divisions and moons emerged, but the basic nature of the rings remained deeply uncertain. Were they solid, fluid, or composed of separate objects? A rigid ring might seem plausible at first glance. Yet, gravity made such a structure difficult to maintain. If a solid ring were perfectly centered around Saturn, the slightest disturbance could pull one side closer to the planet. Gravity would then act more strongly on that side, increasing the imbalance until the ring collided with Saturn. Some astronomers proposed that the ring might be offset in mass or supported by special conditions, but these solutions became increasingly strained. A continuous liquid ring created different instabilities. The structure could not simply behave like a gigantic flat plate suspended in space. In the 19th century, the problem became the subject of one of the most elegant arguments in planetary science. In 1857, the University of Cambridge announced an essay competition asking for a mathematical explanation of the stability of Saturn's rings. James Clerk Maxwell, then a young Scottish physicist, took up the challenge. His analysis showed that neither a completely solid ring nor a uniform fluid ring could remain stable under realistic conditions. The only convincing solution was that the rings consisted of an enormous number of separate particles, each independently orbiting Saturn. Together, they could appear continuous from a distance, just as a cloud appears solid, even though it is made of countless droplets. Maxwell's conclusion was mathematical rather than observational. No telescope could yet resolve the individual ring particles. Still, the equations predicted a hidden reality. The rings were not an object, but a population, a vast orbital swarm whose members continuously passed around the planet according to the same gravitational laws that guided moons and planets. This changed the meaning of the ring system. It was no longer a decorative band attached to Saturn. It was a dynamic environment filled with motion, collisions, gaps, waves, and countless pieces too small to see from Earth. Decades later, spectroscopy provided direct support for Maxwell's reasoning. In 1895, James Keeler studied the light from different parts of Saturn's rings and found that the inner regions moved faster than the outer regions. That pattern is exactly what should happen if the rings are made of separate orbiting particles. Material closer to Saturn must travel more quickly to remain in orbit, while material farther away moves more slowly. A rigid disk would rotate differently, with all parts completing a turn together. The rings, therefore, carried their own unmistakable signature of independent motion. By the end of the 19th century, astronomers understood the broad truth, but almost every important detail remained hidden. They knew the rings were made of particles, yet not what those particles were made of, how large they were, how old the rings might be, or how they had formed. They could see bands across Saturn's atmosphere, but the planet's muted colors concealed much of its weather. They could track moons, yet their surfaces were little more than faint points. Even Saturn's rotation was difficult to measure because it offered no permanent solid landmark. In the 20th century, photography, spectroscopy, radio astronomy, and steadily larger telescopes sharpened the view. Scientists found that the rings reflect sunlight efficiently because they contain large amounts of water ice. Additional moons appeared. Fine structures within the rings suggested that the gravity of satellites was sculpting them. What once looked smooth became crowded with narrow bands, ripples, and gaps, each hinting at invisible interactions. Yet, Earth remained too far away for certainty. Atmospheric distortion blurred the smallest features, and the rings themselves often concealed the regions scientists most wanted to study. Saturn had changed from a wandering star into a planet, from a planet into a ringed world, and from a ringed world into an entire system governed by delicate gravitational relationships. Every improvement in vision had made it less simple. The obvious next step was also the most difficult. Instruments would have to leave Earth, cross the darkness between the planets, and examine Saturn from close range. Only then could humanity discover whether the elegant world imagined through telescopes was truly calm, or whether the pale clouds and shining rings were hiding something far more violent underneath. When spacecraft finally reached Saturn, the planet did not become easier to understand. It became stranger. Cameras could map clouds, instruments could measure gravity, and radio signals could pass through the upper atmosphere, yet the world beneath remained hidden behind a veil no lens could penetrate. On Earth, the interior of a planet can be imagined in familiar layers: a crust underfoot, a mantle below it, then a core. Saturn refuses that clean arrangement. Begin at the visible cloud tops and move downward, and there is no sudden border where atmosphere ends and planet begins. The hydrogen simply grows denser. What starts as a thin gas is compressed into a hot fluid, and deeper still, it enters states of matter that have almost no everyday equivalent. Saturn is therefore less like a solid globe wrapped in weather, and more like an enormous gradient, a world whose identity changes continuously with depth. At the altitude scientists use as a reference level, pressure is roughly comparable to sea level pressure on Earth. But this is a mathematical convenience, not a surface. Drop beneath it, and the surrounding gas becomes heavier, warmer, and more opaque. Molecules collide more often. Light fades. The upper layers are dominated by molecular hydrogen and helium, with smaller amounts of methane, ammonia, water, and other compounds. Yet even those familiar names can be misleading, because chemistry under Saturnian pressure does not behave exactly as it does in a laboratory at room temperature. A substance that forms a cloud in one layer may dissolve, react, or disappear into a deeper mixture below. The deeper interior cannot be photographed directly, so scientists rebuild it indirectly from the planet's mass, shape, heat, magnetic field, gravitational pull, and the motion of its rings. Every model is an attempt to turn invisible pressure into a physical map. NASA describes Saturn as a gas giant without a true surface, made largely of gases above liquids deeper down. But the word liquid should not make us picture a quiet underground ocean with a shore. Under increasing pressure, molecular hydrogen is forced into a dense fluid state, and the distinction between gas and liquid becomes less useful than it is on Earth. At first, hydrogen molecules still preserve their paired structure, two atoms bound together. Far below the clouds, pressure begins to distort that arrangement. Electrons become less tightly associated with individual molecules, and hydrogen is expected to behave more like an electrically conducting metal. It does not turn into a shining block like iron. It remains a hot, compressed fluid, but one capable of carrying electrical currents. This metallic hydrogen region matters because moving conductive material can generate a planetary magnetic field. In Saturn, however, the magnetic field is unusually symmetrical, with its magnetic axis almost perfectly aligned with the rotation axis. That alignment complicates the usual explanation of how the planet's internal dynamo works. One possibility is that a stable layer above the dynamo filters out irregular magnetic features, leaving the remarkably smooth pattern measured outside. Models have suggested that a helium-rich, stably layered region could play that role, though its thickness and exact structure remain uncertain. Helium may be doing more than shaping the magnetic field. As Saturn cooled over billions of years, helium could have become less soluble in metallic hydrogen, separating into droplets and sinking toward greater pressure. The phrase helium rain sounds delicate, but this would be rain on a planetary scale, occurring in darkness under pressures millions of times greater than those at Earth's surface. As the droplets fall, gravitational energy is converted into heat. This process may help explain why Saturn emits more energy than it absorbs from the Sun, and why it has cooled more slowly than simpler models once predicted. Yet, the details depend on the behavior of hydrogen-helium mixtures at conditions that are extraordinarily difficult to reproduce. Experiments and quantum calculations continue to refine where separation begins and how the material behaves. The broad idea is physically plausible and widely used in models, but the actual scene inside Saturn remains beyond direct observation. The most dramatic revision concerns the core. For generations, diagrams showed Saturn with a small, compact center made of rock and ice, surrounded by neat shells of metallic and molecular hydrogen. That picture was useful, but it may have been too tidy. Material that fell into the young Saturn during formation would have encountered intense heat and pressure. Ice would not remain as ordinary ice. Rock might partially dissolve or mix, and heavy elements could spread outward instead of settling into a sharply bounded sphere. The result could be a diffuse central region in which the proportion of rock and ice increases gradually toward the center, rather than changing at a single edge. Evidence for such a structure came from an unlikely place: Saturn's rings. The planet vibrates. Those internal oscillations slightly alter its gravitational field, and the changing gravity pushes and pulls on ring particles, creating spiral waves. In that sense, the rings act like a seismograph suspended in space. Researchers studying these waves found that some of Saturn's oscillations are split in ways suggesting a large region deep inside that resists ordinary convection. A 2021 model interpreted the signals as evidence for a diffuse core extending to roughly 60% of Saturn's radius and containing about 17 Earth masses of rock and ice. Those values depend on the model and should not be treated as a final anatomical measurement. But the conclusion is profound. Saturn's core may occupy much of the planet, rather than sitting as a small ball at the center. This blurred core changes how Saturn's history is read. A sharply layered planet suggests that heavy material sank efficiently and remained separated. A diffuse center suggests incomplete mixing, gradual erosion, or a primordial composition gradient preserved from formation. Perhaps the young planet swallowed solid bodies that dissolved as they descended. Perhaps its original core was compact and later mixed outward. Perhaps the deepest layers never became fully convective because heavier material below lighter material created a stable arrangement that resisted overturning. Each possibility carries a different story of how Saturn grew and cooled, and the present data do not force every detail into one answer. Cassini's final orbits tightened those constraints by flying between Saturn and its innermost rings, where the spacecraft's radio signal allowed researchers to detect minute changes in velocity caused by gravity. The measurements showed that Saturn's gravitational field could not be explained by a motionless set of concentric layers alone. The atmosphere's east-west jet streams extend far beneath the visible clouds, carrying enough mass to alter the gravity field. An influential 2019 analysis placed the depth of the differential rotation at about 5,600 miles, or 9,000 kilometers, although newer work suggests the depth may vary strongly with latitude. What appears from space as weather is therefore connected to a deep, moving envelope. The clouds are not a thin, decorative skin. Their circulation reaches a significant distance into the planet before electrical conductivity and magnetic forces help suppress the different rotation rates. Saturn's rapid spin complicates the picture further. It completes a rotation in less than 11 hours, despite having hundreds of times Earth's volume. The result is a visibly flattened shape. The equator bulges outward, while the poles are compressed. This is not merely cosmetic. The amount of flattening depends on rotation, internal density, and how mass is distributed with depth. Scientists, therefore, use Saturn's shape and gravity together. But even its exact rotation rate has been difficult to pin down because there is no solid surface feature to track. Different latitudes in the atmosphere move at different speeds, and the planet's nearly axisymmetric magnetic field does not provide the clear rotating clock available at some other worlds. Ring seismology has produced one of the best estimates, yet the deeper lesson remains. Even the length of a day becomes complicated when a planet has no crust. Deeper still, temperature and pressure climb toward extremes that turn common words into approximations. Water, methane, ammonia, silicates, and metals may exist in high-pressure phases unfamiliar at Earth's surface. Materials could dissolve into metallic hydrogen, separate into compositionally distinct layers, or participate in slow circulation lasting millions of years. Heat does not necessarily escape through one simple conveyor belt. Some regions may convect vigorously, while stable layers trap heat and transport it gradually. Saturn's interior may be dynamic without being uniformly mixed, layered without possessing crisp borders, and fluid without behaving like any ocean we know. That is why a cross-section of Saturn should never be mistaken for a photograph. The colored bands in an illustration are hypotheses made visible, boundaries drawn where nature may provide only transitions. The farther inward we travel in imagination, the less Saturn resembles a place, and the more it resembles a physical process. A continuous negotiation among gravity, pressure, heat, rotation, chemistry, and time. Somewhere in that darkness, hydrogen carries electric currents, helium may fall like rain. Heavy elements fade into a vast, diluted core, and ancient heat continues its slow escape. Above it all, the pale clouds appear almost motionless from the distance. But that calm exterior is only the thinnest readable page of a planet whose deepest chapters have never seen sunlight. And before any machine could dream of reaching those hidden layers, it would first have to survive the violent atmosphere waiting above them. Suppose the descent begins high above Saturn's golden clouds, inside a capsule built far beyond anything humanity has ever launched. The rings spread across the sky like an illuminated continent, but below them there is no continent at all, only a curved atmosphere fading into darkness. At first, the spacecraft would not cross a visible border. Saturn does not begin at a wall or a line. Its outermost hydrogen atoms thin gradually into space, so the moment of arrival would be chosen by instruments rather than recognized by the eye. Then the gas ahead would start to matter. The capsule would be traveling so quickly that even the nearly weightless upper atmosphere would become a threat. Hydrogen would pile up in front of the heat shield, compressed faster than it could move aside, and the temperature around the vehicle would rise violently. The capsule would not burn because Saturn's atmosphere contained flames. It would glow because speed was being converted into heat. A sheath of electrically charged gas could briefly surround it, interfering with radio signals and hiding the craft inside its own artificial fire. This entry would have to be steeper and more carefully controlled than the approach to an airless moon. Yet, there would be no runway waiting below, and no final moment when engines could lower the vehicle onto solid ground. The atmosphere would only become thicker. Once the capsule lost most of its cosmic speed, parachutes might open, though Saturn's winds would seize them immediately. The view outside would still be strangely bright. Sunlight at Saturn is far weaker than sunlight on Earth, but the upper haze scatters it across the planet, producing the soft cream and amber colors seen from orbit. Those colors make Saturn appear gentle. They are the calm face of a system moving at tremendous speed. Near the equatorial region, broad atmospheric currents can race faster than the most powerful hurricanes on Earth, carrying clouds around the planet, without continents or mountain chains to interrupt them. A descending probe would not simply fall straight down. It could be pulled sideways for thousands of miles, spun by turbulence, lifted by one current and forced lower by another. Its path would resemble a leaf caught inside a storm larger than the Earth, except the storm would not pass over a landscape. It would be the landscape. The first recognizable cloud deck would likely contain ammonia ice. From a distance, it might resemble a pale fog, but up close, there would be no peaceful blanket of cloud waiting to receive the capsule. The atmosphere could contain narrow bands of rising and sinking gas, waves moving through layers of different temperature, and pockets of turbulence invisible until the craft entered them. The probe's sensors would sample hydrogen, helium, traces of methane, ammonia, phosphine, and other compounds carrying clues about Saturn's formation. Yet interpreting those measurements would be difficult. A single descent would cross only one tiny region of a planet wide enough to hold more than 700 Earths by volume. If the probe entered an unusually dry or stormy location, scientists might mistake local weather for the global atmosphere. That happened in a different form when the Galileo probe entered Jupiter through a relatively dry atmospheric region. A Saturn probe would need luck as well as engineering. As it dropped below the ammonia clouds, the temperature would rise and the chemistry would change. A deeper layer is expected to contain ammonium hydrosulfide, formed when ammonia reacts with hydrogen sulfide. Farther below, water clouds may dominate. These water clouds would not sit above oceans like those on Earth. They would exist within a deep hydrogen atmosphere, hidden under layers so thick that visible sunlight might barely reach them. There, rising warm gas and sinking cooler material could produce enormous convective storms. Water vapor condensing into droplets or ice would release heat, feeding vertical motion. Electrical charges separating within the clouds could generate lightning far more powerful than the flashes familiar on Earth. The capsule might spend long minutes inside darkness, broken by sudden bursts of light, with thunder transmitted not through ordinary air, but through dense hydrogen under increasing pressure. Yet the strangest feature of the descent would be the absence of any approaching horizon. On Earth, even when an aircraft descends through thick cloud, the ground eventually announces itself through radar, reflected light, or a rising landscape. On Saturn, the radar would find no planetary crust below. It might detect cloud layers, droplets, particles, perhaps complex regions of changing density, but no clean surface waiting at a measurable altitude. The probe would continue downward, while the gas slowly lost the behavior we associate with an atmosphere. Pressure would rise from values comparable to Earth's sea level to tens, then hundreds, then thousands of times that amount. Every scientific instrument would face a different failure. Cameras would become useless as darkness and opacity increased. Parachutes might collapse, tear, or become unnecessary once the surrounding material grew dense enough to slow the capsule naturally. Radio signals would struggle to escape through deeper conductive layers. Batteries and electronics would overheat. Seals would deform. Even a pressure vessel built like a deep-sea submarine would eventually encounter conditions beyond anything available in Earth's oceans. The vehicle would not necessarily fail in one cinematic instant. More likely, the descent would become a sequence of small losses. A sensor would stop responding. A communication channel would weaken. The pressure readings would climb beyond the instrument's calibrated range. The craft might continue transmitting only a simple carrier signal after its main computer failed, and then even that signal would disappear. From Earth, the end would be silent. The spacecraft would still be somewhere inside Saturn, but no one would know its exact condition or depth. If a person somehow made the same journey without a sealed craft, the story would end much earlier. Saturn's atmosphere contains no breathable oxygen, and its upper layers are bitterly cold. A pressure suit could delay the inevitable only briefly, while the violent entry and winds would make an unprotected fall impossible to survive. But inside an imaginary indestructible capsule, the journey reveals something more interesting than simple danger. Falling through Saturn would gradually stop feeling like falling through air. The hydrogen around the craft would become so compressed that it would behave as a dense fluid. The capsule's speed would fall as resistance increased, and at some depth, it might become buoyant if its average density matched that of the surrounding material. Instead of plunging endlessly at high speed, it could settle into a layer and drift, suspended inside the planet. A balloon designed for Saturn would exploit the same principle much higher up. Because the atmosphere is mostly hydrogen and helium, finding a lifting gas is difficult. Ordinary hydrogen would provide little advantage in hydrogen-rich surroundings. A heated balloon or another specialized design might still achieve buoyancy, but surviving the winds, cold, chemistry, and limited power supply would be a greater challenge. Such a machine would not land. It would become a temporary artificial cloud, circling Saturn until its systems failed. If the indestructible capsule were made dense enough to keep descending, the surrounding hydrogen would eventually pass into a supercritical state. Under those conditions, the familiar distinction between gas and liquid disappears. There would be no splash, and no sea surface. Density would increase continuously, while heat and pressure rose together. The capsule would be moving through matter that could flow like a fluid, but was compressed beyond anything found naturally at Earth's surface. Deeper still, the hydrogen would begin conducting electricity as metallic hydrogen. At that point, the planet itself would interfere strongly with communication. The moving conductive material helps produce Saturn's magnetic field, and a capsule entering it would face an environment shaped by vast electrical currents, extreme heat, and pressures capable of altering the structure of atoms and molecules. No known material could remain an intact spacecraft there. Even diamond, often imagined as almost indestructible, would not provide a magical solution. Strength alone is not enough when heat changes chemical bonds and pressure forces matter into unfamiliar phases. The capsule would become part of Saturn's chemistry. Metals, ceramics, glass, and electronics would melt, dissolve, react, or separate according to their density. Heavier material might sink farther. Lighter products could remain suspended or be carried upward by circulation. The spacecraft would lose not only its shape, but its identity. Saturn would not contain a wreck sitting on a buried seabed. It would absorb the probe into layers that are themselves always moving. This also explains why an object could not fall cleanly through Saturn and emerge from the opposite side. In a fictional tunnel through a perfect vacuum, gravity would accelerate an object toward a planet's center and then slow it as it climbed away. Saturn provides no vacuum tunnel. Its atmosphere and deep fluids would remove the object's motion through drag. Long before the center, almost all of the original speed would become heat and turbulence. Whatever remained would settle according to density, perhaps circulating for years, or descending gradually through regions that may not mix efficiently. Even if the central region contains solid or partly solid material, reaching it would not resemble a landing. The temperatures would be comparable to those at the surfaces of some stars, and the pressure would reach millions of times that at Earth's sea level. The idea of extending landing legs at the bottom becomes almost absurd. There is no ordinary bottom, only a point where one extreme form of matter becomes another. The closest real spacecraft has come to this journey was Cassini during the final moments of its mission. In September 2017, after years of orbiting Saturn, it deliberately entered the upper atmosphere. Cassini was not built as a descent probe. It used its thrusters to keep its antenna pointed toward Earth while the atmosphere pushed against it. For a brief period, it transmitted direct measurements from a region no spacecraft had sampled in that way. Then, the aerodynamic forces became stronger than the thrusters could overcome. The antenna turned away, the signal vanished, and Cassini was destroyed higher in the atmosphere than many of Saturn's deeper cloud layers. It never came close to the regions where hydrogen becomes a dense fluid. The most advanced machine ever sent to Saturn survived only the opening moments of the fall. That ending reveals the real meaning of descending into this planet. Saturn would not offer a dramatic impact crater or a final photograph of alien soil. It would erase the boundary between traveler and destination. A probe would enter as a machine and end as scattered material inside a world with no ground, no wreckage field, and no marked location where the journey stopped. Above, the rings would continue turning in sunlight, giving no sign that anything had fallen beneath the clouds. And those quiet clouds, seen from millions of miles away, would continue hiding an atmosphere filled with some of the largest and most persistent storms in the solar system. From a distance, Saturn looks almost too calm to contain weather at all. Its colors are soft, cream, gold, faint gray, and its cloud bands seem blurred beneath a veil of haze, especially when compared with Jupiter's violent reds and browns. But that quiet appearance is misleading. Saturn is not a sleeping world. It is an atmosphere in constant motion, wrapped around a planet rotating so quickly that a full day lasts less than 11 hours. Beneath the pale haze, rivers of gas race around the globe. Storms rise from depths sunlight cannot reach, and enormous vortices turn above both poles. On Earth, weather moves across a solid landscape. Mountains force air upward. Continents redirect winds. Oceans provide moisture, and friction with the ground gradually weakens storms. Saturn has none of those controls. There are no coastlines to break a cyclone, no mountain ranges to block a jet stream, and no rough surface dragging against the atmosphere from below. The weather can circle the planet again and again, carrying energy through a world where the sky does not end at the ground, because there is no ground. Near Saturn's equator, upper atmospheric winds can approach 1,100 miles per hour, or roughly 500 meters per second, several times faster than the strongest hurricane winds measured on Earth. These currents do not blow randomly. They are organized into broad eastward and westward bands, creating a striped pattern that becomes easier to see when spacecraft images are enhanced or taken in wavelengths beyond ordinary human vision. The bands are shaped by Saturn's rapid rotation, which bends moving gas into long flows around lines of latitude. Small differences in temperature and pressure help drive the motion, while huge planetary waves move through the atmosphere, sometimes appearing as ribbons, ripples, or shifting boundaries between adjacent jets. Some of these are related to Rossby waves, the same broad class of atmospheric motion that influences weather systems on Earth. Though on Saturn, they operate across distances large enough to swallow continents. The energy sustaining this circulation does not come only from sunlight. Saturn receives far less solar energy than Earth because it orbits nearly 10 times farther from the Sun. Yet, the planet radiates more energy into space than it absorbs. Heat left from formation, slow gravitational contraction, and processes occurring deep inside continue to warm the atmosphere from below. That internal heat creates an important contrast. Sunlight influences the upper layers and seasons, while energy rising from the interior can drive convection from depths hidden beneath the visible clouds. The result is an atmosphere powered from both directions, with cold sunlight above and ancient planetary heat below. Most of the time, Saturn releases this energy without producing a single obvious global catastrophe. Then, at rare intervals, something breaks through. Astronomers call these enormous eruptions great white spots, though the name understates their scale. They begin as brilliant clouds punching upward through the surrounding atmosphere and can expand until their disturbances stretch around much of the planet. Only a small number have been documented since the 19th century, and historically they have appeared roughly once during a Saturnian year, which lasts about 29.5 Earth years. The timing is not perfectly regular, and scientists are cautious about treating the cycle like a clock, but the pattern suggests that Saturn's deep atmosphere may spend decades storing energy before releasing it in a sudden convective outbreak. The most closely observed example began in December 2010, when a bright storm appeared in Saturn's northern hemisphere. It arrived unexpectedly early in northern spring, rather than near the later seasonal period when some researchers had anticipated such an event. The storm grew with astonishing speed. Its bright head moved through the atmosphere, while a long, turbulent tail spread behind it, eventually wrapping around the planet and colliding with the region where the eruption had begun. At its largest, the disturbance reached a scale comparable to some of the greatest white storms ever recorded on Saturn, with effects extending tens of thousands of kilometers across latitude and much farther around the globe. Seen in visible light, it looked like a brilliant scar cut across the planet's muted clouds. In infrared, it became even stranger. The eruption pushed energy and material upward, changing temperatures high above the visible storm. Warm regions known as stratospheric beacons appeared, and when two of them merged, temperatures in part of Saturn's stratosphere rose dramatically, about 150 degrees Fahrenheit above the surrounding norm, while an enormous vortex formed in the upper atmosphere. The event showed that a storm born far below could disturb layers separated by great vertical distances. Saturn's atmosphere is not a stack of independent shells. A violent eruption in the deeper cloud region can send waves, chemicals, heat, and momentum upward, reshaping conditions high above where the original thunderclouds formed. Water may be crucial to these giant outbreaks. Deep below the ammonia clouds, at pressures far greater than those near the visible cloud tops, water vapor can condense. As warm, moist gas rises and water changes phase, energy is released, giving the storm additional power. Some analyses place the source of the 2010 eruption near a pressure level around 20 bars, deep enough that the clouds responsible were hidden beneath Saturn's outer appearance. The storm was therefore not simply wind blowing across the top of the planet. It may have been the visible eruption of energy stored in a deep atmospheric reservoir. Lightning offered another clue. Cassini detected radio emissions associated with electrical storms, and images revealed bright flashes illuminating cloud systems from within. On Earth, lightning often forms when collisions among ice particles and droplets separate electrical charges inside tall storm clouds. Saturn's exact electrical processes may differ because of its composition, pressure, and scale, but the basic scene could be recognizable. Particles rising and falling through turbulent clouds, charges building until the atmosphere can no longer contain the imbalance. Then a flash powerful enough to be detected by a spacecraft orbiting far above. Yet Saturn's storms are not simply enlarged versions of earthly hurricanes. A hurricane on Earth depends on warm ocean water, moist air, and the interaction between a rotating atmosphere and a solid or liquid surface. Once it moves over land or cold water, its energy supply weakens. Saturn's vortices can remain embedded in atmospheric currents without encountering land. Some may survive for years, carried by jets that preserve them rather than destroy them. Others collide, merge, stretch apart, or fade into surrounding bands. The absence of a surface gives them freedom, but not immortality. They are still shaped by turbulence, differences in wind speed, waves, changing seasons, and interactions with neighboring storms. Nowhere is Saturn's ability to organize chaos more striking than at the North Pole. There, a jet stream follows a path with 6 nearly straight sides, forming the famous hexagon. It spans roughly 20,000 miles, or 30,000 kilometers, across, wide enough to contain multiple Earths, and winds along the jet move at hundreds of miles per hour. It is not a solid structure, a crack, or a mysterious construction. It is a moving pattern in the atmosphere, first recognized in Voyager images and later observed in extraordinary detail by Cassini. Clouds race around its edges, while smaller vortices circulate within it. Yet the 6-sided form has remained remarkably persistent through major seasonal changes. The leading explanations treat the hexagon as a wave trapped within a powerful eastward jet near the pole. Under the right conditions, a flowing current can develop stable bends, just as rotating fluids in laboratory experiments can form polygons rather than perfect circles. Some researchers interpret Saturn's hexagon as a vertically trapped Rossby wave, rooted deeply enough to survive dramatic changes in sunlight. But explaining why the pattern settles so strongly into 6 sides, why it has endured for decades, and how far downward it extends remains an active scientific problem. Cassini also detected a high-altitude hexagonal feature emerging as Saturn's northern hemisphere approached summer, suggesting that the pattern below may influence the atmosphere hundreds of kilometers above it. The hexagon may therefore be less like a line drawn on the cloud tops and more like the visible cross-section of a deep atmospheric structure. At its center turns a different kind of storm, a vast polar cyclone with a clearly defined eye. Cassini images revealed a vortex that resembles a hurricane from above, with clouds spiraling around a dark central region. The eye is about 1,250 miles, or 2,000 kilometers, wide, while clouds around it can reach speeds near 330 miles per hour. The resemblance to an earthly hurricane is visually compelling, but the physics cannot be identical. There is no warm ocean beneath the North Pole feeding the storm, and the cyclone sits almost directly over the planet's rotational axis. It may be maintained by heat rising from below, the surrounding polar circulation, and the way Saturn's rapid spin organizes moving gas. At the South Pole, Cassini found another enormous hurricane-like vortex with a sharply defined eye and towering clouds casting visible shadows, one of the first times such a structure had been observed so clearly on another planet. The poles reveal something important about Saturn. Order and violence are not opposites there. A cyclone can be ferocious yet stable. A jet stream can move at extraordinary speed while holding a geometric pattern for decades. A giant storm can erupt unpredictably, encircle the world, alter the upper atmosphere, and then fade, leaving behind changes that persist long after its bright clouds disappear. Seasons add another slow rhythm to this restless system. Saturn's axis is tilted by about 27 degrees, close enough to Earth's tilt to produce recognizable seasonal changes. But because Saturn takes almost 30 Earth years to orbit the Sun, each season lasts more than 7 years. Sunlight shifts gradually from one hemisphere to the other, changing temperatures, haze, cloud colors, and atmospheric circulation. Cassini arrived during southern summer, watched sunlight move across the equator, and remained long enough to witness northern spring advancing toward summer. Features hidden in polar darkness emerged into daylight. Colors around the North Pole changed. High-altitude hazes formed and faded. Yet the relationship between seasons and storms is not simple. The 2010 eruption arrived earlier than expected, reminding scientists that sunlight may set the stage without deciding the exact moment when Saturn's deep atmosphere releases its stored energy. From millions of miles away, all of this motion is softened into a few pale bands. The violence becomes invisible because Saturn is too large for the human eye to understand at once. A cloud that appears as a small white mark may be wider than Earth. A thin line may be a jet stream spanning the planet. A delicate six-sided figure may contain winds no aircraft could survive. Saturn's calmness is therefore an illusion of scale and distance. Beneath it lies weather without land, hurricanes without oceans, lightning inside clouds buried in hydrogen, and storms capable of disturbing an entire world. But above this vast atmosphere, turning in a plane so thin that it can nearly disappear when seen edge-on, lies an even more precise structure. Billions upon billions of pieces of ice, each following its own orbit, together forming the rings that made Saturn famous. If you could move close enough to Saturn's rings, their perfect appearance would dissolve almost immediately. The broad, luminous bands seen from Earth would no longer look like solid roads of ice. They would become a vast storm of separate objects, each moving around Saturn on its own orbit. Dust grains, shards of ice, tumbling blocks, and hidden bodies large enough to resemble small mountains. Most of the visible ring material is water ice mixed with smaller amounts of darker dust and rock, and the particles range from microscopic grains to house-sized boulders, with some embedded objects possibly reaching kilometer scale. Yet from a distance, sunlight reflected by those countless pieces blends into something smooth enough to look manufactured, as though Saturn had been encircled by a single polished disk. The closer you get, the more beauty gives way to motion. Particles nearer Saturn travel faster than particles farther out, because gravity demands a higher orbital speed closer to the planet. Neighboring pieces continually pass, collide, rebound, fracture, and exchange energy. A human entering the rings would not necessarily face an unbroken wall, because much of the volume is empty space. But predicting a safe path through them would be impossible. Even a small ice fragment moving at orbital speed could destroy a spacecraft. The rings are neither a solid platform nor a peaceful cloud. They are a disc-shaped environment held in balance between gravity, motion, and collision. Their scale is difficult to grasp. The main bright rings stretch across hundreds of thousands of miles, yet much of the A, B, and C rings may be only about 30 feet thick. If the ring system were reduced to the width of a large city, its average thickness would be closer to that of a sheet than a wall. Countless collisions help create this extraordinary flatness. Any particle moving too far above or below the common plane is likely to strike other particles and lose some of its vertical motion. Over time, the swarm settles into Saturn's equatorial plane because repeated impacts erase most motion in other directions. NASA's Cassini measurements show that the main rings are mostly water ice, built from billions or trillions of independently orbiting pieces, while much of the A, B, and C rings is only around 10 meters thick. The familiar labels D, C, B, A, F, and the more distant rings sound like names for separate solid bands, but each is really a region where particle density, composition, brightness, or orbital behavior changes. The B ring is generally the brightest and most massive of the main rings, while the C ring is more transparent. The Cassini division, visible through modest telescopes as a dark gap between the A and B rings, is not truly empty. It contains thin ringlets and scattered particles, but far less material than the bright regions beside it. Darkness does not always mean absence. Sometimes it records the repeated gravitational influence of a moon. Saturn's moon, Mimas, for example, helps maintain much of the Cassini division through orbital resonance. Particles in certain locations repeatedly encounter Mimas's pull at similar points in their orbits. The individual tug is tiny, but repeated over thousands of circuits, it can destabilize those paths and clear material from particular zones. A moon does not need to pass directly through a ring to sculpt it. Gravity can carve from a distance. Smaller moons work more visibly. Pan travels within the Encke gap and helps control its edges, while Daphnis orbits in the Keeler gap and raises waves along the boundaries beside it. Prometheus repeatedly disturbs the narrow F ring, pulling streams of particles outward and leaving dark channels that slowly close behind it. These moons are often called shepherds, but the metaphor can be too tidy. They do not simply guard the rings like fences. They disturb, steal, compress, scatter, and redirect the material around them. Even the roles of Prometheus and Pandora in keeping the F ring narrow remain more complicated than the traditional shepherding picture suggests. Cassini found another sign of hidden bodies in long features shaped like airplane propellers. These structures appear when moonlets too small to clear a complete gap disturb particles around their orbits. Their gravity pushes nearby material inward and outward, producing paired patterns that can extend for thousands of miles. The moonlet may remain invisible, but the ring records its passage. Other features called spokes behave differently. They appear as ghostly radial markings across the rings, sometimes longer than Earth's diameter, then fade within hours. They are thought to involve extremely small, icy particles lifted above the ring plane by electrostatic forces, possibly influenced by sunlight, plasma, and Saturn's magnetic environment. The rings respond not only to gravity, but also to electricity and magnetism. Some of the most revealing images came near Saturn's 2009 equinox, when the sun shone almost exactly along the ring plane. Under normal lighting, the rings look nearly flat because their vertical structures cast little visible shadow. At equinox, even a small object rising above the plane can throw a long shadow across the ice. Cassini then saw ridges and towering disturbances near the outer edge of the B ring, some rising more than a mile above a disk whose ordinary thickness nearby may be only tens of feet. The likely cause was embedded moonlets forcing passing material upward like water splashing around a rock in a fast river. For a brief season of unusual illumination, Saturn's apparently two-dimensional rings revealed a hidden vertical landscape. But the greatest mystery is not how the rings move, it is when they appeared. Saturn formed more than 4 billion years ago, yet measurements from Cassini's final orbits suggested that the main rings have relatively low mass and contain remarkably clean ice. One influential interpretation placed their formation only tens to perhaps a few 100 million years ago, astonishingly recent compared with the planet itself. Under that view, dinosaurs may already have existed on Earth when Saturn acquired something close to its present halo. Measurements of incoming micrometeoroid material also supported the argument that the rings have not been exposed to contamination for the full age of the solar system. If dark dust had been striking them for billions of years and remaining there efficiently, the rings might be expected to look far dirtier. Cassini-based gravity measurements and pollution models therefore produced a strong case for relatively young rings. Yet the case is not closed. Recent impact simulations suggest that much of the dark material from high-speed micrometeoroids may vaporize, become electrically charged, and escape the rings, or fall into Saturn rather than permanently staining the ice. If ring particles resist pollution more effectively than earlier models assumed, their clean appearance may not prove that they are young. The rings could be older than they look, perhaps even ancient, although that possibility must still be tested against their mass, spreading rate, and long-term evolution. The debate matters because each age implies a different origin. Young rings might have formed when an icy moon was shattered by a collision, torn apart after moving too close to Saturn, or destroyed during a major rearrangement of the moon system. One proposed scenario links them to the loss of a former moon, sometimes called chrysalis, whose destruction could also help explain Saturn's axial tilt, although this remains a model rather than established history. Older rings might preserve material from the early Saturn system, repeatedly recycled through collisions so that the particles visible today are younger than the system itself. In either case, the Roche limit is central. Inside this region, Saturn's tidal forces can prevent loosely gathered material from assembling easily into a large moon. Saturn pulls more strongly on the side closer to the planet than on the side farther away, so a weak body can be stretched apart. The same region that destroys moons can preserve their fragments as rings. Preservation, however, does not mean permanence. Collisions grind particles down. Moons exchange material with the rings. Plasma and ultraviolet light charge small grains. Some material spreads outward, some drifts inward, and some falls into Saturn as ring rain. Observations indicate that water-rich products enter Saturn's upper atmosphere along magnetic field lines, while Cassini detected an additional flow near the equator during its final dives. Estimates of how quickly the rings will disappear vary because the loss rate may change with time, particle size, season, and processes not yet fully understood. Under some present-day estimates, the main rings could fade substantially within roughly 100 million years. Other calculations allow longer survival. Either way, their current form is not eternal. Saturn may once have looked almost bare, and some future observer may see only faint remnants where the brilliant bands now shine. That possibility changes the meaning of the view. The rings are not decoration added to a permanent planet. They are an event unfolding across geological time, a structure being created and erased at once. Every bright arc is made of fragments with separate histories. Every gap carries the influence of a moon. Every wave is a record of gravity. And hidden within certain ripples is something even more remarkable: the faint vibration of Saturn itself, transmitted outward until the rings begin to act like an enormous instrument, translating movements deep inside the planet into patterns visible from space. One of the simplest questions anyone can ask about a planet is how long its day lasts. Yet on Saturn, even that becomes strangely difficult to answer. On Earth, we can watch continents turn beneath the sun. On Mars, we can track mountains and craters. Even Jupiter offers atmospheric patterns and a tilted magnetic field that act like rotating markers. Saturn gives us none of those conveniences. Its visible clouds do not move as one solid shell. Winds at different latitudes race around the planet at different speeds, and the deeper interior cannot be seen directly. A bright cloud might circle Saturn in one period, while a neighboring band completes the journey in another. Measuring the movement of the atmosphere, therefore, tells us about weather, not necessarily about the rotation of the planet hidden below. For decades, scientists believed Saturn's magnetic field would provide the missing clock. A magnetic field generated inside a rotating planet usually carries some asymmetry, a slight tilt or irregularity that swings around like a lighthouse beam. Radio emissions linked to that field can then reveal the planet's true rotation rate. Voyager used this method during its encounters with Saturn and measured a period of roughly 10 hours and 39 minutes. The answer seemed secure until Cassini arrived more than 20 years later and found that the radio rhythm had changed. Saturn appeared to be rotating several minutes more slowly than before, an impossible conclusion if the signal truly represented the deep planet. A world as massive as Saturn could not alter its rotation that dramatically in only a few decades. The clock was not measuring what astronomers thought it was measuring. The radio waves, known as Saturn kilometric radiation, are produced when charged particles move through the planet's magnetic environment, especially near the auroral regions. Instead of staying locked to the interior, the timing of these emissions drifts. Cassini discovered that the northern and southern hemispheres could even produce different periods, as though Saturn carried two imperfect clocks, each gaining or losing time with the seasons. Their rhythms gradually approached one another near equinox, then separated again as sunlight shifted between hemispheres. This suggested that conditions high in the atmosphere, winds, electrical currents, seasonal heating, and interactions with the magnetosphere were influencing the radio signal. What had seemed like a direct voice from Saturn's interior was partly an echo shaped by weather and sunlight. The problem became even stranger, because Saturn's magnetic field is almost perfectly aligned with its rotation axis. Earth's magnetic axis is tilted significantly, and Jupiter's is also tilted enough to create a strong repeating pattern as the planet turns. Saturn's field is so symmetrical that its magnetic north pole sits extremely close to its rotational north pole. Cassini's final measurements found no clearly detectable tilt large enough to produce the obvious magnetic pulse scientists had expected. This near-perfect alignment is not merely inconvenient for measuring the day. It challenges standard ideas about how planetary magnetic fields are maintained. Saturn's field is thought to arise from the movement of electrically conducting fluid deep inside the planet, probably in layers where hydrogen behaves like a metal. In most dynamo models, a field that is exactly symmetrical around the rotation axis should be difficult to sustain. Electrical currents created by the fluid motion normally produce irregularities and tilted components. Yet Saturn presents an exterior field that looks remarkably smooth, as though some process has erased the evidence of turbulence below. One possible explanation is that the dynamo itself is not perfectly symmetrical, but a stable layer above it filters out the uneven parts before the field reaches space. A region where helium separates from hydrogen, or where composition changes gradually with depth, might suppress vertical mixing and smooth the magnetic pattern. Another possibility is that Saturn's dynamo operates in a form not fully captured by current models. The available measurements constrain the possibilities, but they do not reveal the machinery directly. Once again, Saturn hides its most important structure behind a calm exterior. Although the magnetic field is weaker at the visible cloud tops than Jupiter's, it controls an enormous region around the planet. This magnetosphere forms where Saturn's field pushes against the solar wind, the continuous flow of charged particles streaming outward from the Sun. On the day side, the solar wind compresses the magnetic boundary. On the night side, it stretches the field into a long tail pointing away from the Sun. The entire structure expands and contracts as solar conditions change, sometimes responding to pressure waves and eruptions launched from the Sun days or weeks earlier. But Saturn's magnetosphere is not shaped by the Sun alone. The planet rotates rapidly, dragging charged particles around with it, and its moons constantly feed new material into the system. The most important contributor is Enceladus. From fractures near its south pole, this small, icy moon releases jets containing water vapor, ice grains, salts, and organic compounds. Some particles join Saturn's broad E ring, while others become ionized by sunlight, collisions, or energetic electrons. Once electrically charged, they are captured by the magnetic field and carried around Saturn, forming a vast cloud of water-related ions. A moon only about 300 miles across therefore influences a magnetic environment millions of miles wide. The magnetosphere is not an empty shield surrounding the planet. It is a moving ecosystem of particles supplied by the solar wind, atmosphere, rings, and moons. These materials do not all travel peacefully together. Freshly ionized particles may initially move at different speeds from the surrounding plasma. Electrical and magnetic forces accelerate them, while collisions redistribute energy. Some particles spiral along magnetic field lines toward Saturn's polar atmosphere. Others are lost to moons or absorbed by the rings, which act like enormous barriers sweeping energetic particles from certain regions. This is one reason Saturn's radiation environment, although dangerous, is generally less extreme than Jupiter's. The rings and moons interrupt the paths of charged particles and create gaps, shadows, and complicated boundaries within the radiation belts. Even here, the famous rings are not passive scenery. They change the space around them. Where charged particles plunge into Saturn's upper atmosphere, they create auroras. From above, these appear as glowing rings around the magnetic poles, shifting, brightening, and sometimes developing arcs or spiral forms. Human eyes would not necessarily see them as the brilliant green curtains familiar from photographs of Earth. Much of Saturn's auroral energy appears in ultraviolet light, invisible without specialized instruments, while emissions have also been observed in infrared and, under some conditions, visible wavelengths. The glowing regions are produced when incoming particles collide with hydrogen in the upper atmosphere, transferring energy that is later released as light. Yet Saturn's auroras are not simple copies of Earth's. Some are driven by changes in the solar wind, but others reflect the planet's rapid rotation and the circulation of plasma inside its magnetosphere. A bright auroral feature can therefore record events occurring far beyond the clouds: pressure from the sun, material from Enceladus, electrical currents flowing through the upper atmosphere, and the turning of the planet itself. Cassini and the Hubble Space Telescope sometimes watched Saturn's auroras together from different viewpoints, revealing patterns that could appear, fade, and shift around the poles within hours. Certain bursts of radio emission rose and fell with auroral activity, reinforcing the connection between the glowing atmosphere and the unreliable magnetic clock. But the relationship was never perfectly simple. The auroras did not behave like hands moving around a clear dial. They changed shape as the solar wind varied and as the northern and southern seasons evolved. Saturn's clock seemed to be written in light, but the writing kept moving. To find the true length of the day, researchers had to abandon the hope of a single obvious marker and combine several indirect methods. They studied Saturn's gravitational field, its flattened shape, atmospheric winds, and the response of the rings to vibrations inside the planet. The ring method became especially powerful. Saturn oscillates in many subtle ways, and those motions cause tiny changes in its gravitational pull. The changes create waves at specific locations in the rings. By measuring those waves, scientists can infer the frequencies of the hidden oscillations and use them to estimate the deep rotation rate. One widely cited analysis produced a day of about 10 hours, 33 minutes, and 38 seconds, with an uncertainty of only a few minutes. That value is shorter than the original Voyager radio period, and is considered one of the best estimates available. But it is still a model-based result rather than a direct reading from a solid surface. Different internal assumptions can shift the answer slightly. Saturn's day has not become unknowable. It has become a lesson in how carefully a measurement must be interpreted when the object being measured has no crust. The question also reaches deeper than timekeeping. Rotation affects Saturn's shape, winds, gravity, interior structure, and magnetic dynamo. A difference of only a few minutes changes estimates of how mass is distributed beneath the clouds. That, in turn, changes models of the diffuse core, metallic hydrogen, and the planet's formation. The length of a day is therefore tied to the history of the entire world. Saturn's magnetism carries the same hidden connections. The auroras reveal charged particles. The charged particles reveal the influence of moons. The radio pulses reveal currents in the upper atmosphere. The field's symmetry hints at unseen layers deep inside. Nothing around Saturn can be studied entirely alone. The planet, rings, plasma, and satellites continuously exchange matter and energy, forming a system whose parts leave fingerprints on one another. And nowhere is that connection more revealing than among the moons themselves, where frozen surfaces, buried oceans, strange ridges, and methane seas preserve chapters of Saturn's history that the planet's own clouds have concealed. Saturn's own clouds conceal most of its past, but the worlds circling around it preserve that history in ice, stone, atmosphere, and motion. Seen from far away, the moons appear like small points scattered beside a giant planet. Yet, together, they form one of the most complicated families in the solar system. Some are massive enough to have atmospheres and hidden oceans. Others are irregular fragments that may have been captured, shattered, or rebuilt. Some sweep material from the rings, while others continuously add new particles to them. Saturn currently has hundreds of confirmed moons, ranging from tiny bodies only a few miles across to Titan, which is larger than the planet Mercury. The number itself can change as astronomers identify additional distant objects. But the deeper mystery is not how many moons Saturn possesses. It is whether all of them belong to the same history. They may instead represent several generations, some born with Saturn, some formed from later debris, and some captured after wandering too close. Titan dominates this family. It is Saturn's largest moon and the only moon in the solar system known to possess a substantial atmosphere. From space, its surface disappears beneath a dense orange haze rich in nitrogen and methane. For decades, that haze protected Titan as effectively as Saturn's clouds protected the planet itself. Telescopes could reveal its size and atmosphere, but not the landscape below. Then, radar instruments aboard Cassini began mapping a world that looked disturbingly familiar. Titan has mountains, dunes, river channels, clouds, rain, lakes, and seas. But its rivers do not carry liquid water, and its rain does not smell like rain on Earth. At Titan's surface temperature, water is frozen as hard as rock, while methane and ethane can flow as liquids. Hydrocarbons evaporate, gather into clouds, fall as rain, run through channels, and collect in northern lakes and seas, creating a climate cycle that resembles Earth's water cycle while operating with entirely different chemistry. This similarity can be more unsettling than complete alienness. Titan shows that a world does not need warm oceans or breathable air to develop coastlines, weather, erosion, and seasonal change. Its surface may look geologically recognizable, yet a person standing there would face temperatures near -290 degrees Fahrenheit, weak sunlight filtered through haze, and an atmosphere unsuitable for breathing. Even so, Titan offers something Saturn never can: solid ground. On January 14, 2005, the European Space Agency's Huygens probe descended beneath the haze for about 2.5 hours, photographing branching channels and rounded pieces of water ice before touching down on the surface. It became the first spacecraft to land on a world in the outer solar system. The probe struck soft ground, bounced, slid, and came to rest, transmitting data for more than an hour after landing. Above it, Titan's sky remained orange and dim. Around it lay ice fragments shaped by processes that may have involved flowing liquid methane. Humanity could not land on Saturn, but it had landed on Saturn's greatest moon. Titan may also hide a deep ocean of liquid water beneath its frozen exterior, although its thickness, composition, and ability to exchange material with the surface remain uncertain. That possibility makes Titan more than a cold chemical imitation of Earth. It may contain two very different environments separated by miles of ice: hydrocarbon seas exposed to the atmosphere above, and a water-rich ocean buried below. Whether either environment could support life is unknown. Titan's surface chemistry may produce increasingly complex organic molecules, but complex chemistry is not evidence of biology. Its value lies in showing how far natural chemistry can develop under conditions unlike those on Earth, and in forcing us to ask whether the ingredients associated with life must always be arranged in the same way. Far closer to Saturn, Enceladus presents the opposite mystery. It is tiny, bright, and coated in clean ice, a moon that once seemed too small to remain geologically active. Then, Cassini observed vast plumes erupting from fractures near its south pole. Jets of water vapor and icy particles were escaping into space from long cracks known as tiger stripes. Instead of needing to drill through the crust, Cassini could fly directly through material coming from below. The plume contained salty ice grains, organic compounds, ammonia, and other chemicals, while gravity and motion measurements indicated that a global ocean of liquid salty water lies beneath the crust. Some of the escaping grains continuously supply Saturn's broad E-ring, meaning that this small moon is slowly scattering part of its interior around the planet. Enceladus became even more compelling when Cassini detected molecular hydrogen and tiny silica particles consistent with hot water interacting with rock on the ocean floor. On Earth, similar water-rock reactions occur around hydrothermal systems and can provide chemical energy used by microorganisms. Later analyses also identified phosphorus compounds and a growing variety of organic molecules in plume material. These findings do not prove that anything lives in Enceladus's ocean. They show that several major requirements associated with habitability — liquid water, useful chemical elements, organic chemistry, and possible energy-producing reactions appear to exist in the same hidden environment. The distinction matters. A habitable place is not necessarily an inhabited place, and Cassini was not designed to detect life directly. Yet few discoveries have changed the search for life more profoundly, because Enceladus demonstrated that a small frozen moon far from the Sun can maintain an active ocean and deliver samples of it into space. Then there is Mimas, a moon whose enormous Herschel crater gives it the appearance of a damaged mechanical sphere. Its heavily cratered surface suggests age and inactivity, especially beside the fresh fractures and plumes of Enceladus. Yet measurements of Mimas's slight wobble have produced evidence that it may contain a buried ocean, although some interpretations have instead considered an unusually shaped core. More recent research has strengthened the ocean possibility, potentially placing liquid water beneath roughly 15 to 20 miles of ice. If that interpretation is correct, Mimas may possess one of the youngest internal oceans known, formed relatively recently as tidal heating changed its interior. But no plume has been observed, and there is no direct sample of the hidden material. Mimas remains a warning against judging a world by its surface. An ancient-looking crust may cover a body that is still changing inside. The contrast between Mimas and Enceladus is difficult to ignore. They are similar in size, and both experience Saturn's gravitational influence. Yet one sprays its ocean into space, while the other appears silent. Differences in orbital history, ice thickness, internal structure, and tidal heating may explain the divide, but there is no single answer accepted in every detail. Perhaps Enceladus was driven into a more active orbital resonance. Perhaps Mimas began heating much later. Perhaps the difference is temporary, and we are seeing the moons at separate stages of a cycle that unfolds over hundreds of millions of years. Saturn's moons do not merely display different outcomes. They may reveal different moments in the evolution of icy worlds. Farther out, Iapetus carries history across its surface in black and white. One hemisphere is coated in dark material, while much of the other is dramatically brighter. The moon is locked so that the same side leads along its orbit, allowing it to sweep up dark dust that may originate largely from distant Phoebe. Once a region darkens, it absorbs more sunlight and warms slightly, encouraging surface ice to vaporize and migrate toward colder, brighter areas. This feedback may have intensified the two-faced appearance over time. Iapetus also possesses a towering ridge running along much of its equator, giving it a shape unlike any other major moon. The ridge may have formed from material belonging to a former ring around Iapetus, from internal forces early in the moon's history, or through another process not yet fully resolved. Each explanation accounts for part of the evidence, but the ridge still resists a universally accepted origin. Hyperion is stranger in an entirely different way. It has an irregular, sponge-like body, covered with deep craters and an unusually low density, suggesting abundant empty space within its structure. Rather than rotating steadily with one face toward Saturn, Hyperion tumbles chaotically. Its orientation cannot be predicted far into the future because small differences in its motion grow over time under the gravitational influence of Saturn and Titan. The moon turns as though it has forgotten which direction should be up, providing one of the clearest natural examples of chaotic rotation. Rhea, Dione, and Tethys appear more orderly, but their icy surfaces also preserve evidence of bombardment, tectonic fractures, radiation, and the exchange of material within Saturn's system. Dione's bright, wispy terrain was once thought to be surface deposits, but proved to be great networks of cliffs and fractures. Tethys carries the enormous Odysseus crater and a canyon system stretching across much of the Moon. Rhea is heavily cratered and may possess a tenuous exosphere created when energetic particles strike its icy surface. Color differences across these moons reveal how charged particles and material moving through Saturn's magnetosphere slowly alter them, so even an apparently dead surface continues to interact with the planet around it. The smallest moons make the boundary between moon and ring particle seem almost arbitrary. Pan and Daphnis orbit inside ring gaps, disturbing nearby particles and raising waves along the edges. Atlas accumulates loose ring material around its equator, giving it a broad ridge and a shape sometimes compared to a flying saucer. Prometheus repeatedly pulls strands from the narrow F ring. Enceladus feeds the E ring with its plumes, while Phoebe contributes dark dust to an enormous faint outer ring. Matter moves from moon to ring, and from ring toward moon, suggesting that these categories are stages rather than permanent identities. A moon can be broken into a ring, and ring material can gather into moonlets when gravity and tidal conditions allow it. That exchange leads to the largest unanswered question in the system. Did Saturn's major moons all form with the planet, or was part of the family created later? Some models suggest an early disk of gas and debris produced generations of moons, many of which migrated inward and were destroyed. Other scenarios propose that collisions among earlier satellites created the present rings and rebuilt some of the inner moons from fragments. The regular, nearly circular orbits of the large inner moons suggest formation within a disk around Saturn, while the distant, irregular moons often follow tilted or backward paths consistent with captured bodies. But arranging every moon, ring, resonance, and chemical signature into one timeline remains difficult. Saturn's family may not have one birthday. It may be the surviving result of repeated construction, migration, collision, capture, and loss. The planet cannot show us its earliest layers directly, but its moons carry pieces of the missing record. Titan preserves atmosphere and organic chemistry. Enceladus exposes an ocean. Mimas conceals change beneath an ancient face. Iapetus collects dust from distant space. Hyperion reveals chaos in motion. The smaller moons shape the rings that may contain the remains of worlds no longer present. Together, they turn Saturn from a single planet into an evolving system, one that could only be understood after a spacecraft remained there long enough to watch its parts interact, and then, when its fuel ran low, made the final descent into the world where no machine could ever land. By the time Cassini arrived, Saturn had already been visited 3 times, but never truly watched. Pioneer 11 passed the planet in 1979, followed by Voyager 1 in 1980 and Voyager 2 in 1981. Each encounter lasted only days. The spacecraft raced through the system, captured what they could, and continued outward, leaving behind images that transformed a distant point of light into a world of braided rings, strange moons, violent weather, and unanswered questions. Those flybys were like opening a door for a few seconds and trying to understand an entire house from the glimpse inside. To learn how Saturn changed with seasons, how its moons interacted with its rings, and what might be hidden beneath its clouds, humanity needed something far more ambitious: a spacecraft that could enter orbit and remain there for years. Cassini-Huygens began that journey on October 15, 1997, rising from Cape Canaveral aboard a Titan 4B rocket. It was one of the largest and most complex interplanetary spacecraft ever launched, created through a partnership between NASA, the European Space Agency, and the Italian Space Agency. The machine carried an orbiter named for Giovanni Domenico Cassini and a landing probe named for Christian Huygens, linking the mission to the astronomers who had first begun revealing Saturn's true form centuries earlier. Yet even a powerful rocket could not send such a massive spacecraft directly to Saturn. Cassini had to borrow momentum from other worlds, flying past Venus twice, returning near Earth, and then passing Jupiter. Each encounter bent its path and increased its speed through gravity, turning the planets themselves into part of the spacecraft's propulsion system. The route stretched across nearly 7 years and billions of miles. But on July 1st, 2004, Cassini reached Saturn and fired its main engine for more than 90 minutes. The burn slowed it just enough for Saturn's gravity to capture it, making Cassini the first spacecraft ever to orbit the ringed planet. The arrival was dangerous. Cassini crossed the plane of the rings through a gap where large particles were considered less likely, turned its antenna forward as a shield, and passed closer to the planet than it would again for years. Then the engine ignited, and the spacecraft disappeared behind Saturn from Earth's point of view. Mission controllers could do nothing but wait. When the signal returned, Cassini was no longer a visitor passing through. It had become Saturn's artificial moon. What followed was not a single exploration, but a long relationship between a machine and an entire planetary system. Cassini repeatedly adjusted its orbit using Titan's gravity, passing close to moons, crossing the ring plane, climbing above the poles, and returning to regions from new angles. The European Huygens probe separated in December 2004 and descended through Titan's atmosphere the following January, while Cassini remained above to receive and relay its signal. That landing became one of the mission's defining achievements, but it was only the beginning of what the orbiter would uncover. Its cameras watched storms form and disappear. Radar pierced Titan's haze and revealed lakes and seas of liquid hydrocarbons. Instruments flew through Enceladus's plumes and found material connected to a salty underground ocean. Cassini observed the North Polar Hexagon emerging from winter darkness, studied lightning in giant storms, mapped the rings at scales never seen before, and measured how charged particles flowed through Saturn's magnetic environment. It arrived during southern summer and stayed long enough to watch the seasons shift through equinox and toward northern summer. A mission originally planned to spend 4 years at Saturn was extended twice because the spacecraft remained healthy and the system kept revealing new questions. Cassini's success, however, created a problem no mission could avoid forever. Its electrical power came from the slow decay of plutonium, but its movements depended on a limited supply of propellant. After years of steering, stabilizing, and correcting its orbit, that fuel was running low. If engineers eventually lost control, Cassini could wander unpredictably through the Saturn system. It might strike Titan or Enceladus, worlds now considered scientifically important because they contain environments where complex chemistry and perhaps habitable conditions could exist. The spacecraft had been sterilized according to planetary protection standards, but it had not been cleaned thoroughly enough to guarantee that no hardy microorganisms from Earth remained aboard. The chance of contamination was remote, yet the consequences could reach far into the future. A terrestrial microbe surviving on an ocean moon could confuse later experiments or interfere with an environment humanity had barely begun to understand. Leaving Cassini in an unstable orbit was therefore not considered responsible. Engineers could have sent it away from Saturn, but that would have sacrificed one final opportunity. Instead, the team chose an ending that transformed destruction into exploration. Cassini would be deliberately placed on a path into Saturn, ensuring that it could never threaten the moons. Before it died, it would enter a region no spacecraft had ever crossed, the narrow gap between the planet and the innermost edge of the main rings. The grand finale began in April 2017, after a close encounter with Titan reshaped Cassini's orbit. Over the following months, the spacecraft completed 22 plunges through the approximately 1,500-mile-wide space between Saturn and the rings. Before the first crossing, no one knew with complete certainty how much dust or debris waited there. Even tiny particles could be dangerous at Cassini's speed. The spacecraft turned its large dish antenna in the direction of travel, using it as a shield while instruments sampled the environment from behind it. The gap proved quieter than many had feared, but not empty of scientific surprises. Cassini measured Saturn's gravity with extraordinary precision, helping researchers estimate the mass of the rings and examine the depth of atmospheric winds. It sampled particles falling from the rings into the planet and searched for the small tilt in Saturn's magnetic field that might reveal its true rotation. It photographed the rings and cloud tops from angles impossible during earlier phases of the mission. Each orbit brought the spacecraft close to destruction, then carried it back into space, as though Saturn were allowing Cassini to approach the edge 21 times before finally refusing to let it leave. The last orbit began with a distant pass by Titan on September 11, 2017. Mission engineers called it the goodbye kiss, because Titan's gravity gave Cassini the final push needed to guarantee atmospheric entry. There would be no later correction and no path back to orbit. During its remaining days, Cassini transmitted stored images and prepared its instruments for direct sampling. Cameras were shut down before the plunge because images required storage and later transmission. During the final descent, the priority was live scientific data. The spacecraft turned its antenna toward Earth and held that position while its mass spectrometer tasted Saturn's upper atmosphere. At a distance of roughly 900 million miles, the final radio signals needed about 83 minutes to reach Earth. Everything Mission Control received had already happened more than an hour earlier. On September 15th, Cassini entered Saturn's atmosphere approximately 1,190 miles above the level conventionally called the cloud tops. The surrounding gas was extremely thin, comparable in density to the tenuous atmosphere near the orbit of the International Space Station. But Cassini was moving at about 76,000 miles per hour. At that speed, even traces of hydrogen exerted enough force to push against the spacecraft. Cassini's thrusters began firing to prevent the craft from turning away from Earth. At first, only a small correction was needed. Then, the atmosphere thickened. The thrusters worked harder, climbing toward full output as they fought to keep the antenna aligned. The machine had spent years using those engines for delicate adjustments. Now, they were being asked to resist an entire planet. For a brief time, Cassini continued sending measurements while the aerodynamic pressure increased around. Saturn reminds us that some worlds were never meant to be touched, only understood from afar. Thank you for listening, and please subscribe to Sleepy Cosmic Lore for more quiet journeys through the universe.